All right, so let's take a look at section 11.5. Okay, 11.5 is on what we call induction. Okay, and basically induction is a way to prove things. Okay, it's all proofs. It's very different, though, than the kind of proofs you did in geometry. We're not writing statements, reasons, and doing a two-column kind of thing. Okay, this has a structure to it, but it's also a very predictable structure. When you're doing like a statement reason proof, sometimes you don't know what the next statement is. You know, is it parallel lines cut by a transversal, or is it alternate interior angles or vertical angles? It's kind of hard to figure out where to go with the proof. This isn't hard to figure out where to go. It's pretty much the same thing each time. It's just getting used to thinking the way this proof works. Okay. First thing is, with induction, we're not using this to figure out anything new. Okay? Induction is used when you have something you already think is true, like a formula. And you say, you know what, I think this is the right formula for the problem, and it should work. This would prove it works. All right? So induction is just a way of verifying something that you already have to be true. You're not going to use this to discover something new. I think I have an example like from last week. Okay, this is the sum of the first n perfect squares. Okay, and last week I told you this was the formula. Well, if you wanted to prove that this was the formula, we can, using induction. Okay, that's how we would prove that this formula is correct. But you already have to have this formula to start with. Okay, you can't prove something you don't have. So on a test, I would give you what's on the left, I'd give you what's on the right, and I would say prove that what's on the right actually works. Okay, just kind of as a quick review, let's make sure, remember how to use these kind of formulas. So if you wanted to know what the first, let's just do the first three. Okay, what the first three perfect squares added up to. All you have to do is plug in 3 for n. And it should be the same as adding up the first 3. Okay, what do the first 3 perfect squares add up to? Augustine?
16.
Let's see. So we got 9 and 4 gives me 13, and then one more. 14. So if you add up the first 3 perfect squares, you get 14. Okay, let's try plugging 3 into this formula and see if we get 14. Okay, 3 times 3 plus 1 times 2 times 3 is 6 plus 1 is 7. Divide by 6. Okay, we can reduce that. Divide by 3. Divide by 3. And we get 1 times 4 is 4. 4 times 7 is 28. And 28 divided by 2 is 14. Okay, so the formula, it kind of looks like it might work. At least we know it works for the first 3. But we want to prove that it works in every case. Okay, any value you picked for n. Okay, so any questions on that? All right, so these are the kinds of problems you'd use induction for. Okay, first thing I'm going to do is just describe to you a set of numbers. I'm going to give you 2 characteristics about this set to kind of get you to start thinking inductively a little bit. Okay, so this set has 2 properties. Okay, first thing I'm going to tell you is that the number 1 is in the set. Okay, the number 1 is in the set. The second property I'm going to tell you is that if k is in the set, then k plus 1 is in the set. Right, so together we can kind of put those 2 facts together and figure out what numbers are really in this set. Right, so I'm telling you 1 is in the set. And then the second thing I'm saying is if k is in the set, then k plus 1 is in the set. I would think they can tell me what kind of numbers are in my set. How about Kobe? Can you tell me something that I know is in the set? Guaranteed.
1.
1. 1 is in the set. Now, reading the second statement, it says if something, okay, K, if something is in the set, then the one after it is in the set. Does that help a little bit? That's all this notation says. If something is in the set, then the one after it is also in the set. So what else is in the set? Yeah? 2. Now read statement 2 again. If something is in the set, then the one after it is in the set. So what else is in this set? 3. So basically, what is set S? It consists of all the what? How would you describe these numbers?
All the numbers possible in the set.
So I'm looking specifically, like, how would you characterize like the numbers 1, 2, 3, 4, 5, up to infinity? Like they're not fractions. That's a hint.
Would it be as elements of S?
They are all elements of S, but they're specific kinds of numbers. Like they're not decimals. They're not looking for the right word.
All positive integers.
All positive integers. Perfect. So what numbers are in S? I'll put all positive integers. And the reason we started with 1 has to do with when we start proving formulas. 1 is the first term. 2 is the second term. 3 would be the third term. That's how we number the terms in a sequence. We don't start with the 0th term or the negative second term. We start with the first one is the first term, okay, and so on. It's all positive integers. All right, so I'm going to write down basically kind of an outline of how you do induction. Okay? Don't get too concerned if you're kind of confused looking at it, because when we go through an example, I'll break it out step by step. So when you do any kind of proof with induction, okay, the first thing is you have to know your formula works for a base case, okay, or the basis. It's kind of like your starting point. What we usually do is we let n equal 1 as our starting point. Now, at the beginning of class, I proved to you that a certain formula worked. I think I let n equal 3. We generally don't go that high. Okay, we start with n equals 1. Right, so if we go back and look at that formula we just had, okay, I'll put this right back up. We'd take this formula. We'd say, okay, here's the first term. If you add up the first term on the left side, you get a 1. Now plug 1 in for n and make sure that the right-hand side also comes out to 1. And if they do, then we just prove that the formula works, at least for the case where n equals 1. Now you could do when n equals 2 or n equals 3. You could go as high as you want. But the problem is you can't go as high as you want forever. I mean, if you want to prove it works for every single number, you can't check every single number forever. That's not the way to go about it. So we check 1, and that's our starting point. Okay, it's called the base case. Bless you. Okay, now the next step, some people have a little bit of trouble understanding or accepting why you can do this. After you prove it works for the base case, you're allowed to assume that the formula would work for any specific value up to k. Because basically what we're assuming here is we could say, if we wanted, we could check it for n equals 1. We could check it for n equals 2, for n equals 3, n equals 4. We could check it as high as we want. Okay? But we're not going to keep checking it. We already checked it for 1, and it worked. So what we're going to do is just assume that it would work up to a particular value of k, where k is a positive integer. And honestly, even if the formula didn't, well, if it didn't work, you wouldn't have anything to prove. But even if it didn't work, you at least know that it works for one value, because you're going to check that. Okay, so you have your starting point. Okay, but the next step is where the induction really comes in. Okay, we're going to assume that it's true up to a particular value. Okay? But we want to show that it's true for the one after. Okay? So we're going to assume it works up to k, but then we have to show that it works for k plus 1. And this is where the induction comes in. Because if it's true, say, for every number up to 5, and then you can show it's true for the one after 5, then it's true for 6. And if it's true for the one for 6, and it's always true for the one after, you kind of get this domino effect. All right? So think of it as you've got your dominoes. You show that it's true for the first one. Okay, you knock that one over. And then it's going to knock over every one after that, because it's always going to be true for the one after. Okay? Kind of like thinking of the numbers in that set S earlier. Does everyone understand why you can't plug in infinitely many numbers for n and just check them all by hand? There's too many to check. It'd kind of be like if you had 1,000 dominoes and you just keep taking one out at a time, okay, right off the side. You just keep pulling them out. Well, it's going to take a very long time to get rid of them that way than if you just knock one into the other and then they'll knock themselves down rather than taking them out one at a time. Okay, there's too many to check that way. All right. So let me show you, here's an example of something we could check with induction. Okay, it's a very simple formula. It just gives you the sum of the first n integers. So in other words, if you want to add up the first 5 integers, in theory, you should be able to just plug 5 into the right-hand side. And it should tell you what 1 plus 2 plus 3 plus 4 plus 5 is, without doing all the work out. First thing we do is just make sure that this formula works when n equals 1. Okay? That's your base case. All right, so if we add up the first 1 integers on the left-hand side, well, it's not very interesting. It's just the first term, 1. And now we're going to plug 1 into the right-hand side and make sure it works. Right, so we get 1 equals, if we do 1 plus 1, okay, that gives me 2 times 1 is 2. And then divide 2 by 2, we get 1 equals 1. So we know that this formula does work for the case when n equals 1. Okay, any questions on that? Now I could check it for when n equals 2, and I should get, when I plug 2 in, should get the sum of the first 2 terms. Okay, you should get 3. And if you check it, 2 plus 1 is 3. 3 times 2 is 6. 6 divided by 2 gives me the sum of those 2 numbers, 3. We could check it up as high as we want. So we're going to assume that this formula would work up to a particular value, k. Okay? Not all the way up to n. We don't know if it works that far. But we're going to assume that it would at least work up to a certain point, k. Right? Okay, and I'm not going to go all the way to n. I'm going to stop before n. Okay, k is some number before n. And we're going to assume that this formula works at least for this small section. Okay, maybe k is only like 8. Okay, so maybe this formula only works up to 8. Maybe that's as far as we checked it. But maybe n is 10,000. So we haven't checked it that far. Okay, so we're just going to assume that it works up to k, some fixed point. Any questions on that step? Here's the induction part. We want to show that instead of just adding the numbers up to k, let's add the next one in and prove that the formula still works if you go to the one after. Okay? So we have 1 plus 2 plus 3 plus all the way to k plus, what's the term that comes after k? Yeah?
K plus 1.
K plus 1. Okay, at this step, all you do is take what you had right here, fill in k plus 1, and then write it right after it. That's all you do. Okay, so that's the left-hand side. If we add on one more term after k plus 1. Now, on the right-hand side, this is the formula that tells you what the first k integers add up to. How would this formula change if you were adding up the first k plus 1 integers? What would happen to all my k's? Like if I was adding up the first 6 integers, these would be k would become 6's. If I was adding up the first 20, the k's would become 20's. If I was adding up the first k, it would look just like this. What about if I was adding up the first k plus 1 numbers? Yeah?
Would it become K plus 1
Yeah, that's part of it. K plus 1.
times
Mhm.
would it be K plus 1 plus 1
Yep.
plus 2?
Yeah, so we could write k plus 2. We'll do that in the next step. Right, so now on the right-hand side, we're using our formula, not just to go up to k, but we're using it to go to the next one after it, which would be k plus 1. So fill k plus 1 into your formula on the right-hand side. K plus 1 times really k plus 2. Divide by 2. Now, if we add on the next term, the k plus 1th term, and we plugged k plus 1 into our formula, and both the left and the right-hand sides come out the same, then we're good. If they don't come out the same, then we have a problem. Okay. So next thing you want to do on the left-hand side, you got to get rid of this dot, dot, dot. We already know what everything from here all the way to here adds up to, based on what we just did up above. What do all the numbers from 1 to k add up to? What does our formula up above say they add up to? Darren?
K squared plus k over 2.
Okay, yeah, we might want to distribute that out at some point. For now, I'll just leave it. But yes, we'll probably end up distributing that. So if you want to add up everything up to k, well, it adds up to this. Well, if you want to add the next one in, just write it down. And in theory, if you add everything up to k, plus the one that comes after it, it should add up to what this right-hand side says. Because this was the formula that was given. All we did was take the formula we were given and plug in k plus 1 as the variable to add up the first k plus 1 terms. All right. Now, at some point, we need to start doing this out. Or maybe if we're clever, we could, instead of foiling all this out and foiling all this out, maybe we could factor the left-hand side to make it look like the right. Okay. However you can make the left and right-hand sides match, that's the goal. A lot of people just distribute it out. All right, so for this one, I'll do it the way Darren had mentioned. So if you distribute out, you get k squared, bless you, plus k. Now, what's my common denominator going to be? Oh, Andy? 2. So I'm going to multiply top and bottom by 2. Okay, I just want to combine these into a single fraction. I'm going to get 2k plus 2. Okay, now that's all divided by 2. Okay, and at the same time, I'm going to distribute out what's on the right. And I think at this step, you'll see that they are the same. Okay, k squared plus 2k plus 1k plus 1 times 2 is 2. Lastly, just combine your like terms. And that'll show that what's on the left and the right is the same. It's k squared plus 3k plus 2 divided by 2. And on the other side, it's also k squared plus 3k plus 2. So what we just showed is that the formula will work for the one after k. So now, if you have a number that you know it already works for, which we do, the base case, we just showed that the formula will always work for the one after that one. Okay? We know it works for 1 and the one after 1. So now we know it works for 2. And it always works for the one after. So it works for 3, it works for 4. That's what we just proved. Right, so our last step, now we can say we have shown, and it's just the original problem. So that's your very last step. Just write down, we've proven, or we have now shown, and write the original question. Okay, that's the idea of inductive proof. And that's as simple as I can make it. There's nothing I can do to make it any easier. Any questions on what we did there? Okay, I think it takes a while for people to kind of wrap their head around what they're doing. Even after this week, a lot of people can go through these steps and they can do it fine, but they don't really understand what they're doing or exactly why they're doing it. That's the part that I can't really explain to you. All of a sudden, like, you do enough of these and it just clicks all of a sudden. It's like, oh, okay, now I see what I'm doing. Okay. But we'll try a couple more. What can happen though is if you try to FOIL this out, the algebra can start to get kind of messy. Depends on how complicated the original problem was. Okay. This one, it's no worse than a quadratic. Okay, but there are some that start to get a little worse. But the steps don't change. It's the same steps. Okay, let's try this one. So this one is just adding up the first n. How would you say this? How could you basically explain what you're adding up here? Forget what it adds up to. That's the formula. We'll prove that. Just explain what's on the left-hand side. James?
You just say the first n odd numbers.
Yeah, you're just adding up the first n odd numbers. First 10 odd numbers, the first 50 odd numbers, however many you want to add up. And what I'm telling you is that they add up to n squared. If you wanted to add up the first 10 odd numbers, I guarantee you they add up to 100. Okay, so I've given you the formula. First thing we're going to do, show that it works for the base case. Okay? This is kind of like knocking over that first domino. Show that it works in one spot. Then we'll assume that it works for any particular value we want to check up to k. We're not going to check them. We could check them. But we're just going to assume that it works. And then we'll show it's true for k plus 1. Okay, Victoria, if I'm going to show this works for the case when n equals 1, what's the sum of the first 1 terms on the left-hand side? Yeah, just the first term, just 1. And fill in 1 into the formula on the right. And obviously that is true. Keep checking the base case when n equals 1. Sometimes it seems a little too easy. It usually is easy. If you wanted to check it for something a little higher, try, in your head, just to try it. Don't write it down. Try it when n equals 3. So the sum of the first 3 odd numbers should be 9. And it is. Any question on showing that it works for the base case? All right. Now assume that it works up to a particular value of k. We don't know if it works all the way up to n, but at least we know that it works up to some value k. And if nothing else, we at least know that it works up to 1. Okay, we at least know it works up to 1. You've got to be careful with your kth term here. It's a little more complicated than just a k. It's a 2 times k minus 1. In the last problem, it was just a k. So when we filled in for k plus 1, it was pretty straightforward. Just be careful on this one. Now we want to show that this formula is going to work for the one after k, k plus 1. So we've got 1, 3, 5. Okay, that's up to the kth term. What would be the k plus 1? Bless you. What would be the term after this? The k plus 1 term. Okay, so this is how you generate each term. If you want the first term, you do 2 times 1 minus 2. If you want the sixth term, 2 times 6 minus 1. 50th term, 2 times 50 minus 1. Kth term, 2 times k minus 1. How about the k plus 1th term? Yep.
2k.
Well, is that how I'm generating my terms? Are they just 2k?
Oh, no. It'd be 2k plus 1 minus 1.
Yep. And it does make a difference. Those plus 1s, minus 1s don't quite cancel. You'll see why in a second. So this is the term that you want. So if you want the k plus 1th term, plug in k plus 1. Okay, so this is adding everything up to k and the one that comes after it now, k plus 1. Okay, what should I put on the right-hand side? Because now we're not adding just up to the kth term, we're adding up to the k plus 1th term.
K plus 1 squared.
Right. This is the part we don't know if this is true. Is this going to work for the one after? Okay, well, we're about to check. Okay. First thing I have to do is get rid of the dot, dot, dot. So on the left-hand side, I know that everything from 1 up to what adds up to something. What can I basically get rid of on this side? Every number from 1 up to basically going to do a substitution, just like we did last time. Okay, so I took all this stuff and I substituted something in for it. The only thing I can't substitute in is the new term I added on the end. Okay, so what could I substitute in for here? Cool.
K squared.
And what's going to change to k squared? Everything from 1 up to what?
2k minus 1.
Good. Okay, we already know what everything from 1 up to 2k minus 1 adds up to. That was from our assume step. Okay. Everything up to there is what Cole just said. It all adds up to k squared. And now we're going to add the term after. Okay. What I'm going to do is, let's do this out. 2k plus 2 minus 1. So 2k plus 2 minus 1, that's 2k plus 1. Okay, and we're going to see if it equals that. I think the easiest way, just distribute out the right-hand side. So we get k squared plus 2k plus 1. Okay, this is using our assume step and then adding on the next term. And then on the right-hand side, this is using the formula they gave me. And we're testing to see if it works. Okay, so we're kind of doing the same thing two different ways. One with what we assumed, one with the formula they gave us. And sure enough, if you do this out, it comes out the same no matter which way you do it, which proves their formula works for the next term. Question? So when I distribute out, I get 2k plus 2. And then 2 take away 1 just gives me a plus 1. And that's basically it. Okay, so now for your last step, just write down what you just proved. Write down we have proved or we have shown, and then just put the original problem. So now we know that our formula not only works up to k, but it'll always work for the one after k, and the one after that, and the one after that, and the one after that. It goes on forever, as high as you want to go. Okay, any questions on that one? Okay, anyone want to see one more of this, kind of the simple type? Yep. All right, so I'm going to have to make one up. So what we'll have to do is we'll make up a pattern, see if we can figure out the formula for it, which you wouldn't have to do that part of the test. Then we'll prove what we think the formula is to be correct. Right? So we got to make it up. There is one in the book, but the exponents start to get like 4th and 5th powers, so the distributive property becomes awful. And we have to use binomial theorem. It just takes a while. All right, so let's see if we can come up with a pattern for adding. Okay, we did perfect squares. Did we do perfect squares? Let's try perfect squares. Okay, because actually I think we can. We have that in our notes. Okay, we can look up the sum of the first n perfect squares. The book does perfect cubes, and that gets a little messy. All right, so. Okay, so we're adding up perfect squares, 1, 4, 9, 16, 25. Okay, I think we had one with something squared, but this is a little different. Okay, does anybody have that formula? I wrote it as a sigma, and there were 4 of them. We had integers, perfect squares, perfect cubes, and then I think we had a constant. And this one, I had a denominator of 6. Anyone have, Cole, you've got that? I think one might have been an n plus 1 or a 2n plus 1. Yeah.
It would be n times, in the parentheses, n plus 1. And the other parentheses, 2n plus 1.
And it's over 6, right?
Yeah.
Okay. Okay, so first thing we want to do, show that this formula works for the base case. Okay, so I'll just copy this. Okay, I'm going to show on paper that it works for the base case, but then in my head, I'm going to check it for maybe when n equals 3 and make sure we get the right number. Okay, we haven't done this one yet, right? Today? Just making sure, 149. No. This might have been the one actually. Yeah, it's the one I gave you in the notes that said, here's an example of something you could prove with induction, but we didn't actually do it. So now we're going to do this one. So show that it works for n equals 1. Okay. Alex, if I add up just the first perfect square on the left-hand side, what do I get? 1. Just the first term. Just 1. Okay. Now let's see if you plug 1 into the formula, if that works. So I plugged in a 1 everywhere that I had an n. So I'm going to get 2 plus 1 is 3. 3 times 2 is 6. 6 times 1 is 6. And I've shown that this formula at least works if you plug in n equals 1. Okay, who can tell me my next step? Okay, proved it for the base case. What do I do next? James?
Do you do or put k or this?
Right, we're going to assume that this formula works for any value up to k. So let me just copy that. Oops. Okay, so assume that our formula works for any particular value up to k. Can't assume that our formula works all the way up to n. We don't know that, because we only checked one base case. We could check 2, 3, 4 base cases if we want, but at least we know we have one that works. That's why we're allowed to do step 2. If you didn't have a base case, you can't assume anything. Okay? The only reason we can assume is because we know that it works at least up to when k is 1. Okay? At least we know it works that far. It's not very far, but it's a starting point. Right, so change all your n's to k's. Is it 2k plus 1? Yeah. And this you can write equals. There's no question mark here. We're assuming that this does work because we showed the base case. The next part, we're going to show that it works for k plus 1. Okay, so show that your formula you just wrote up above is going to work for the one after the one you just wrote. Okay, anybody think they can tell me how the left-hand side is going to change if I add on the next term after k? So I'm going to have everything I have here plus one more term, the k plus 1th term. Yep?
After you put in the plus k plus 1 squared,
Anything that's going to come before that?
well, you're going to replace all that with the big formula on the right.
Right, so I'm going to copy all this down first, right? Yeah. So we've got 1 plus 4 plus 9. So we're adding everything up to k, plus we're going to add one more term. And what's that next term we're going to add?
K plus 1 squared.
Good. So you're going to add your first term squared, your second term squared, third term squared, fourth term, fifth term, kth term squared, kth plus 1 term squared. And now, James, what should that equal?
The big formula of the k plus 1.
So I'm going to copy all of this. Well, this only adds everything up to the kth term. We got to extend this formula a little bit and see if it works to the k plus 1th term. So what would you have to fill in for all your k's?
So k plus 1.
Right. Okay, if you wanted to know what the first 20 numbers add up to, fill in 20 for k. The first 1,000, fill in 1,000 for k. The first k plus 1, fill in k plus 1 for k. So we're going to have k plus 1 times k plus 1 plus 1 times 2 times k plus 1 plus 1. 2k plus 1 plus 1. So all I did was plug in k plus 1 for all the k's. And this is a question mark. We don't know if this formula works for anything after k. We know it works up to k. We got to show that it works after that. And then if it works after, it works forever. Okay, James already gave us a hint at our first step. I'm going to replace everything up to k squared with what our assumption step was. Okay, so we got k plus 1, 2k plus 1 over 6. It's k plus 1 squared over 1. On the right-hand side, why don't, let's distribute out and combine some like terms so we can at least simplify it a little bit. K plus 1. What's the second factor going to be? What's k plus 1 plus 1? Emily? How do we simplify that? So we have k plus 2. And how about this third term? Yeah?
2k plus 3.
Right. 2k plus 2 plus 1. Okay. So 2k plus 3. Okay, and this all has a denominator of 1 if you want to put it for now. Just to put everything with a denominator. Okay, now the goal is to make the left-hand side and the right-hand side look the same. Okay, there's a couple ways you could do it. One way, which most people do, just kind of like brute force, do everything out. Just multiply all this, multiply all that, find a common denominator and add them up. If you are a little clever about it, you might be able to do some factoring on the left-hand side to make it look like the right-hand side, which is already factored. Right. That part, a lot of times people have trouble with because the factoring is a little more complicated than normal. But we could try it either way.
How come you didn't do like the whole long equations over 6? Like we were doing before.
The whole long equation.
Like on the end.
On this part? Oh, should it be? Thank you. Yes. The denominator doesn't change. It stays exactly the same as what it has been. Thank you. That would have messed us up. Okay, so which way do people want to try it? You want to try just distributing, foiling everything out and combining like terms? Or trying to be clever about factoring somehow? Well, let's try the factoring way, okay, and see if we can make something work. If we can't factor it, then we'll go back and we'll do all this out. It's just going to be a little messy to do out. Okay. What would your common denominator be between the two terms on the left? 6. Okay, so for now, I'm just going to try to work with the left-hand side and somehow factor it to make it look like the right. So I would multiply by 6 and 6. I'm not going to rewrite that whole thing just to add in the 2 6s. Okay, I'm just going to leave it like that. Now, if you look at your first fraction and second fraction, okay, it's one big denominator of 6 now. What do they both have in common in the numerators? Yeah, they both have a k plus 1. Okay, this has k plus 1 squared. This has k plus 1 to the first. We can factor out a k plus 1 from both of them. Okay, let's try that and see if we start to get something that looks like this. If we don't, we'll go back and we'll just FOIL everything out. So if I factor out a k plus 1, okay, here that would leave me with a k and a 2k plus 1. So we factor out the k plus 1. All I'm left with is a k and a 2k plus 1. Okay, plus here it would leave me with a 6, and it would leave me with a k plus 1. I factored one of them out. Okay, well, we have the first factor, k plus 1. K plus 1. So now it's just a matter of, can we make all of this come out to k plus 2 times 2k plus 3? That should be pretty simple. Just distribute this out, it'll become a quadratic, and then see if it factors as k plus 2, 2k plus 3. And then we're done. Okay? But don't mess with this. You've got the k plus 1, you've got the k plus 1, leave it. See if we can get the rest of it. All right, so we have k plus 1. I think, yeah, since we're going to do this out, we can get rid of the brackets now. 2k squared plus k plus 6k plus 6. That's still over 6. Okay, combine your like terms. You're going to get 2k squared plus 7k plus 6. And we're hoping that that part factors into k plus 2, 2k plus 3. Let's just try it and see if it works. And then we'll check it. Okay. Well, we know anyway it would have to be a 2k and a k. We know our signs would have to be plus, plus. We need two numbers that multiply to give us 6. So we'll try 2 and 3. So that'd give me 2k squared plus 6k. Let's see, does that?
Mr. Hager,
Yeah.
when you were factoring out the k plus 1 up top, when you factor out k plus 1 from 2k plus 1, don't you just have k plus 1 left?
From here?
You took k plus 1 from that whole top line,
Yep. So this is gone.
and then you took it away from 2k plus 1 as well.
So this is gone.
You have like 2k plus 1, wouldn't it factor out of that too? Because you were multiplying and not adding?
Well, we factored out, let me just make sure I crossed out the right things. So we factored out k plus 1 from here, right?
You wouldn't take it away, you wouldn't factor it out of the 2k plus 1 too?
You can't. Nope. Because it's a different factor. You can only factor out something that's identical to what in both spots. There's no 2k plus 1 over here. It's kind of like if I said, you know, what number can you factor out, you know, from both of those? Well, whatever you factor out has to be identical in both spots. You could try to take a 4 out, and it would come out of one of them, but it wouldn't come out the other one, because these aren't both multiples of 4. Try to factor a 4 out of that. You can't, unless you're going to use fractions.
No, never mind. That wasn't what I was saying, but just.
Well, you're asking me, where were we? When I factored out k plus 1, why didn't I take it out of 2k plus 1?
Yeah.
It's basically like saying, why didn't I take the 4 out of the 3? Because I can't. Because it's not a common factor. 3 is not a multiple of 4. 2k plus 1 is not a multiple of k plus 1. Does that make sense?
Yeah.
This is not a multiple of that. So you can't factor it out. So now, let's see, I lost where we were. So yeah, we factored out k plus 1. Okay. So this is gone. This is gone. Right, so we have k, 2k plus 1, that's fine. Okay, we have 6 and k plus 1. All right, so far we're good. K plus 1, that's fine. It's 2k squared plus k. That's 6k plus 6. Okay, we combined our like terms. We had 2k squared, that's 1k, and 6k is 7k, plus 6. And then we were checking to see if this worked when we factored. Okay, does that work? I just guessed at putting the 2 and 3 in those spots. Does that come up to that? Cody? Don't get hung up on the factoring, guys. This is going to really slow us down for the induction. You've got to make sure your factoring and foiling is solid. Just foil that in your head and see, check it. If that comes out to that. That should be quick, Darren? No. So when you factor, if that didn't work, try switching the 3 and the 2. I kind of already know what the answer should be, but I'm trying to factor it kind of like I would in Algebra 1, pretending like I'm guessing and I didn't know what it would be. So now if I check it, see 2k squared plus 4k plus 3k, that's 7, and 3 times 2 is 6. So if you factor the left-hand side, that's what you get. If you factor the right-hand side, that's what you get. And if I can get them on the screen at the same time, you'll see they're the same. K plus 1, 2k plus 3, k plus 2. So the left and the right sides come out the same. Okay, don't let the algebra part start to trip you up, because then that's going to make the induction, you're going to think you're doing something wrong with the induction, because I'd imagine at this point most of you aren't confident yet with the induction. Okay, so you have to be confident with your algebra. Can't have any mistakes in the algebra. It's hard, but it has to be perfect. Okay, any question on that one? So now your last step, just write down what you've proven. We have shown. Put down the original problem. And that was n plus 1 to n plus 1. If you didn't like factoring it, you don't have to do it this way. Foil everything out here. K plus 1 times k plus 2 times 2k plus 3, you'll end up with some cubic. Foil everything out on the left-hand side, and you'll end up with another cubic, and make sure they match. That'd be another way to do it. Okay, so those are the kind of problems where you're proving something about a series. Okay, here's one where you're proving something about an explicit formula. Okay, so they give you a recursive formula. They're telling you what the explicit formula is. They want you to prove that this is correct. Question? Okay, how would I show that the formula works for the base case? What do I have to plug in? James?
4.
What number are we? Well, not necessarily what the first term is, but what would n be in the base case?
Oh,
1. You have to show that this and this come out the same. If you plug 1 into your explicit formula, do you get the first term in sequence A? Well, they give me the first term in sequence A. It's a 4. Okay, so that's left-hand side is what they gave me. Right-hand side is the calculation using the explicit formula. 3 times 1 is 3. 3 plus 1, 4. So this formula does give me the first term in sequence A. That's the base case. Any question on the base case? Okay, after I show that it works for the base case, what do I show next? Or what do I write next? Yeah.
The case over that one plus 1, like 10 plus 1.
Well, not k plus 1 yet. It's something we want to write down before that. But that's what we're going to want to prove in a second. Show that it works for the one after k.
For anything with the guy.
Right. This formula, we're going to assume it works for anything up to k. Not all the way up to n. Maybe just up to k, whatever that happens to be. Okay, so now we're going to assume a sub k equals 3k plus 1. Okay, we want to show that it works for k plus 1. So the k plus 1th term should be generated like this. should be able to just plug in k plus 1 for k, do it out, and that should give you the term you're looking for. So that's the result we're hoping to get somehow. How is the k plus 1th term generated? Now we can't go back and just say, oh, we just used the explicit formula. We already did that right here. This is the part we're hoping is true. All right, so this is what we're hoping is true. How would you generate the k plus 1th term based on the formula they gave you? Not the explicit formula, but the recursive formula. What did the recursive formula say to do? Mhm.
If you plug in 2,
Do what? Take the...
if you plug in 2 to the formula, see.
Here's your recursive definition. What does that mean to do? Yeah.
3 plus the term 4.
Perfect. Take 3 plus the term before it. Can you tell me how that would work if I wanted the k plus 1th term, Darren?
Something plus the term after it.
Nope, exactly what you said. It's 3 plus the term before it. So 3 plus, what's the term before a sub k plus 1?
3k plus 1.
Okay, yes, that's true. I'm going to write that in a second. But what is 3k plus 1? This is the k plus 1th term. This is the kth term. Okay, so to find the term you want, take 3 plus the 1 before it. Now this is our substitution step. Okay, just like we've been doing before. Okay, we're going to substitute in. This time we don't have a dot, dot, dot. Okay, that was for a series induction problem. This is just a sequence. So we're taking 3 plus the term before it. Okay, so this is generated using, I'll just write this here. Use the recursive definition to write this down. So we know this is true. This is not a guess. This is using exactly what they said to do. Take 3 plus the term before it. Okay, the term before it, that comes from our assumption step. Okay, it's 3k plus 1. 3k minus 1. That would mess us up a little bit. And now combine your like terms. Okay, 3k plus 3 plus 1, we get 3k plus 4. So using the recursive definition, we get 3k plus 4. Using the explicit formula and hoping that it worked, we should have gotten 3k plus 4. And we did. Okay? So they both come out exactly the same. So this kind of problem feels a little bit different than the series problem. But it's the same idea. And that's it. Now just write down what you've shown. We have shown that that's how you generate the nth term in the sequence. Any question on that one? All right, let's see. Okay, so somebody give me a sequence recursively. Can be anything you want. Don't make it too challenging and don't make it depend on the two previous terms. Only make it depend on one previous term. Because that would be a little different if it depended on two. Oh, cool. And you know what? Put a, pick one where you multiply the previous term by something and then add a number. But don't make it too big. Pick a number from 1 to 5. Not 1. I can't multiply by 1, it won't work. 2. So 2 times the previous term. And then let's do minus something. Pick another number. Minus 3. Okay, so here's a sequence. Okay, let's list out the first few terms. I gotta give you a starting term. Let's let the starting term be 4. Okay, let's list out the first few terms, see if we can come up with the formula, and then prove that that formula is correct. Okay, what would my next term in that sequence be? Darren? 5, good. Okay, we're just doing this to try to maybe figure out the pattern. So we got 4, 5. Next term in that sequence, James?
7.
Let's see, 2 times 5 is 10, minus 3 is 7. And let's do one more. Darren? 11. Let's see if we can come up with a pattern. Okay, you know what, let's do one more. Okay, first thing I'm going to do is check just to see if it's a polynomial pattern. I'll look at the differences and see if I can find a pattern here. Okay. 5 minus 4 is 1. 7 minus 5 is going to give me 2. 11 minus 7, that's going to give me 4. And what's 19 minus 11? 8. Okay, so there's a pattern. So the next difference would probably be 16. So what's happening is since the number is doubling each time, it's probably never going to come out to a row of constants. It's always going to be coming out to 1, 2, 4, 8. Okay, it's always just going to double each time. So it's not a polynomial pattern. So that's what happens when you make up an example. Let's see if maybe we can just figure out what it is. Does anybody see what you do to the number in red to get the number below it in blue? If not, what I'll do is I'll take the 2 away from the a sub n minus 1, and that'll make the pattern a lot easier. I'll get rid of the 2. It's not going to be easy to come up with, I don't think. Anyone think they see it? If it was just doubling each time, maybe, let's see. Well, it doesn't look like it's definitely not arithmetic because you're not adding the same number each time, and it's not geometric because you're not multiplying the same number each time. So we can't use either of those tricks that we already have. So what I think I need to do, let me just simplify it. Thought we could pick a small enough number and it would be easy, but it's still pretty hard. Okay, let's just take the first term, or take the term before and subtract 3. Okay, this should make it a lot easier. So first term is still 4. Second term now would be, subtract 3, you get 1. Negative 2, negative 5, negative 8. Anyone see what the pattern is for that now? Remember, what kind of sequence is this? Because we're subtracting the same number over and over. Is that arithmetic or geometric? It's arithmetic, so we have a formula that gives us that automatically. A sub n is equals a sub 1 plus n minus 1d. We don't even have to guess. We'll just use that formula from last week. Right, so it should be 4 plus n minus 1, and this time the common difference is negative 3. Subtract 3 each time. So let's say we have 4 minus 3n plus 3. So it should be negative 3n plus 7. Let's check and see if it works. So 2 times negative 3 is negative 6, plus 7 is 1. Yeah. 4 times negative 3 is negative 12, plus 7 is negative 5. Okay, so it looks like this is the formula that would work. Okay, I'm going to leave that for you to finish proving inductively. So now you're basically at this step. You've got the first term, you've got the recursive formula, and you have the explicit formula. You're going to now do it the same way. But that's the hard part, just getting this formula. Proving it, it's going to be exactly like the last one you did. All right, so let's see. What I'll do, since I gave you that one, let's just get rid of that one. Right, so do 1 through 7. And the last example. Okay, on 1 through 7, okay, it's page 624. Ignore the directions they have. Do exactly what we've been doing in class. You just prove that using induction. There's 4 problems that are about sequences, just like the last one we did in the notes. And then 3 problems like we did in the beginning of class. In fact, one of them, I think number 5, we've already done. I did that as an example. Okay, so we'll take a look at that tomorrow.